we present a new approach for multimodal learning that handles the audio-visual modality relevance, which is still a big challenge in computer vision and video understanding. A lot of videos on the web are audio-visual irrelevant and thus leads to inaccurate recognition of human activities. So leveraging the relevant audio and completely dropping the irrelevant modality is a key solution. So how can we perform this without having audio-visual annotated datasets? First, we adopt language models such as BERT to map the video dataset labels to their most key relevant audio labels in the audio datasets. This will generate a label dictionary, which is then used in the training phase. To get an overview of the entire proposed framework, let's start with the default two-stream vision transformer, where we use two visual modalities, the RGB frames and the optical flows. This two-stream transformer uses late fusion to aggregate the visual representation from both transformer encoders. The output of the visual stream is then passed to the proposed IMD and then to the final classifiers. Simply, this scheme, except the IMD module, is the well-known approach for training two-stream video models. Now, to add the audio modalities, we use the log spectrogram as an input to the audio transformer, which is frozen to keep the original knowledge of the audio datasets. We add an audio bottleneck to bridge the semantic gap between the audio knowledge and the current training datasets. Now, as we have audio and visual modality, we propose the IMD to estimate their relevance. The relevance network is a learnable MLP, whereas the next is a non-parametric network that decides to fuse or to drop the audio modality. To create a ground truth for training the relevance network, we use the overlap of the predicted audio and the recommended audio classes from the semantic label dictionary, which is then used to compute the binary cross entropy. Finally, the weighted loss is used to optimize all trainable parts of the framework. This part is the only part used in the inference phase, whereas these two parts are used in the training phase. Here is the proposed IMD in more details. Relevance network is an MLP that receives the audio-visual embeddings and provides the relevance scores, whereas the modality dropout module decides whether to use the audio modality or to drop it. The proposed method has shown better performance as compared to the relevance method on both audio-visual modality fusion and human activity recognition, in particular on large video datasets such as Kinetics 400. Generally, we proved that language and audio models can be leveraged to improve the video understanding. Since our framework is a transformer-based framework, it shows better performance on large datasets. IMD performance relies on the quality of the pre-trained audio models. Assessing the quality of the semantic label dictionary can be further improved through introducing a better label matching evaluation metric.